Welcome back. In the last episode, we looked at the landscape of AI agents and talked about how they have all converged on a shared grammar. But if you actually pull down the repositories and read the source code for these tools, you will find one massive fork in the road.
Yes, it is a single, fundamental design choice that every harness builder has to make on day one. And this one choice effectively decides everything else about the tool, especially which brains you can successfully put in the jar.
When you use a coding agent, the magic moment is when your code actually changes on your screen. But getting from the model's text generation to a modified file is surprisingly complex. Today, we are going to unpack the 3 dominant ways harness builders solve this problem.
Quick, honest note before we dive in. This is an education series, not advice of any kind. We are just two curious people trying to make AI make sense.
And AI moves fast, so everything here is how things work as of 2026, and it will keep changing. Treat it as a map, not gospel. The real learning happens when you go and try it yourself. The problem every harness has to solve is this. Once the model has decided what code needs to change, how does it actually deliver that edit to the file on your hard drive?
Remember the core constraint here. The model is just a brain in a jar generating text. It cannot physically reach into your computer and press the backspace key on your keyboard. The harness has to take the model's text output and translate it into a concrete file system operation.
And across all the open source tools we mapped out in episode 8, there are really 3 dominant schools of thought for how to accomplish this. We have parsed text, native tool calling, and grammar-constrained hybrids.
The method a harness chooses dictates exactly what kind of model it requires. It is the ultimate expression of our rule. The harness sets the floor. Let's look at the first school of thought. Let's start with parsed text. This is the approach famously used by Aider, which is arguably one of the most reliable and beloved tools out there right now.
In this school of thought, the model writes its edits as plain text directly into the chat response, using a very specific formatting convention. The harness then uses regular expressions and heavily optimized custom parsers to scrape that text, interpret the intent, and apply the changes.
Aider is actually brilliant here. By default, it uses a very forgiving whole file format where the model just rewrites the entire file from top to bottom. Because there is no complex diff syntax to mess up, this easy format allows even weaker models to successfully make edits.
Exactly. And this is a crucial nuance. Aider does not switch formats based on runtime weakness detection. Instead, capable models are explicitly upgraded via configuration to a diff format known as search replace. For strong models, the model outputs a block of text saying, search for this exact chunk of code and replace it with this new chunk. The parser is the secret sauce here. It has to be incredibly robust to handle when the model hallucinates a line break or messes up the indentation.
The second school of thought is native tool calling. You see this heavily utilized in tools like OpenCode and Hermes, and it is becoming increasingly standard for newer agents.
Instead of asking the model to format plain text that a parser has to carefully scrape, the harness exposes a strictly typed function, like an edit file tool, using JSON schema. The model natively calls this tool, passing in the file path, the lines to replace, and the new code as JSON arguments.
It is incredibly clean from an engineering perspective. There is no messy text parsing or regular expressions to maintain. You just receive a JSON payload, validate it, and execute the file rewrite.
However, it completely relies on the model being exceptionally good at structured output. If the model is bad at writing valid JSON, if it forgets to escape a quotation mark or messes up a bracket, the tool call fails and the entire system collapses. And finally, we have the third school, the grammar-constrained hybrid. A perfect example of this is OpenAI's Codex CLI and its apply RPatch tool.
This approach attempts to get the best of both worlds. The harness exposes a native tool call framework, so the agent is formally using tools to act. But inside that specific tool, the actual code change payload is passed as a freeform patch text.
It uses a strict grammar constraint. The model says, I am calling the applies patch tool, but the content it sends is a unified diff or a block of standard patch text.
It requires the model to understand the deep grammar of code patches, like context lines and exact line numbers. but it bypasses the need for the model to perfectly escape every single character inside a massive JSON string. It blends the formal structure of a tool call with the flexibility of text. If you're wondering why we are getting into the technical weeds on parsing versus JSON versus patches, this is why. This single choice largely decides which models a harness works well with.
It is the setup for everything you do next. If a harness uses strict native tool calling with large JSON payloads, you simply cannot use a small, local model that struggles with JSON formatting. The harness will just throw validation errors all day long.
Conversely, if you use a harness with a very forgiving parsed text approach, like Aider's default whole file format, you can plug in almost any model, and it will work reasonably well. The parser absorbs the model's structural mistakes.
It perfectly illustrates our core concept. A robust parser lowers the floor so weaker models can participate in the loop. A strict JSON tool call raises the floor, demanding a top-tier model but offering cleaner execution.
While we are reading the source code of these harnesses, there are two more absolute gems we have to highlight. The first is Aider's repo-map.
When an agent needs to understand your entire massive codebase, how does it do it? Many people assume it uses heavy vector databases and embeddings, but Aider's repo-map doesn't use embeddings at all. It uses a tool called treesitter to tag all the functions and classes, and then it runs a PageRank algorithm, the exact same math that powered early Google, to rank the most important files. It is incredibly efficient.
The second gem is from Hermes. Hermes has implemented a remarkable self-improvement loop. After every single turn, the agent takes a moment to reflect and write durable memory to the disk.
It constantly updates its own understanding of the codebase conventions and your specific preferences. Over time, the harness actually makes the brain smarter by giving it better context on the next lap. Let's recap. When handing an edit to the computer, you have three options: a marked-up printout, which is the parsed text approach, a structured form, which is native tool calling, or a strict fill-in-the-blanks patch, which is the grammar-constrained approach.
That single choice determines exactly what kind of brain you need to put in the jar. And speaking of brains, we are finally ready for the ultimate question.
In episode 10, our series finale, we're going to talk about natural couples. We're going to look at what happens when you try to run these models entirely on your own machine at home, and why memory bandwidth is the true bottleneck.
We will see you in the finale. And that is a wrap for today. If this made AI feel a little clearer, do us a favor and subscribe. It genuinely helps more curious people find the show.
We are learning and building with AI right alongside you, one episode at a time. So hit follow, and we will see you in the next one.